Good afternoon, everyone. My name is Jyoti from BSc Chemistry Honors Final Year. My roll number is 76. Today's my topic is hard and soft acid and bases. The term acids and bases are routinely used in our daily life. Chemists have been classifying substances as acid and base since long time. Lavoisier noted that common elements in all acids was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy showed later that all acids contain hydrogen. It was in 1884 Arrhenius developed the theory of acids and bases, known today popularly as Arrhenius theory of acids and bases. According to Arrhenius, an acid is a substance which can give hydrogen ion in aqueous solution, and a base is a substance which give hydroxyl ion in aqueous solution. The strength of an acid or a base depend upon its capacity to provide H positive and OH negative ions respectively. The process of neutralization of an acid by a base can be represented by the reaction H positive plus OH negative gives H2O. In 1923, J.N. Bronsted and T.M. Lowry independently proposed a new acid-base theory. According to their theory, an acid is a proton donor, whereas a base is a proton acceptor. The acid-base reaction, i.e. the neutralization, is regarded as proton transfer reaction. In 1923, J.N. Lewis gave another general definition of acid-base behavior in terms of electron pair donation and acceptance. However, this theory got the recognition only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. In the other word, an acid is an electron pair acceptor while a base is an electron pair donor. The earlier definitions of acids and base were solely based upon the observable properties such as taste, ability to dissolve substances insoluble in water, and their effect on vegetable dyes. The term acid was applied to the substances that have a sharp to or sour taste, turn blue litmus red, react with certain metals to liberate hydrogen gas, and have the ability to dissolve substances insoluble in water. On the other hand, term base was applied to the substances that have a bitter taste, soapy feel, turns red litmus blue. However, tasting and feeling chemicals are dangerous method of determining whether the substance is an acid or a base. You should never ever taste or touch solution of chemicals in laboratory. There are, however, other methods of recognizing acids and base. For example, acids and bases changes the color of certain dyes, popularly known as indicators. One of the most common indicator is vegetable dye obtained from lichen known as litmus. Aqueous solution of acid, the litmus red, whereas aqueous solution of bases turns it blue. Thus, any substance which has an unshared pair of electrons can act as Lewis base, whereas a substance which has an empty orbital to accompany a pair of electrons, such as Lewis acid. In other words, substances capable of donating a pair of electrons are regarded as Lewis bases, and substances capable of accepting a pair of electrons are regarded as Lewis acids. Acid-base or neutralization reactions may thus be regarded as donor-acceptor reaction or coordinate covalent bond formation reaction. The classical example of Lewis acid-base is the reaction between boron trifluoride and ammonia. Using electron dot diagram, we can see that boron trifluoride is the Lewis acid and ammonia is a Lewis base. Lewis concept of acid and bases is very commonly used because of its simplicity and ease with which the formation of coordination compound can be explained. In brief, all the usual ligands can be regarded as Lewis bases, whereas the metal ions can be regarded as Lewis acids. The degree of affinity of a metal ion for the ligand can be termed as Lewis acidity, and the tendency of ligand to combine with metal ion can be regarded as Lewis basicity. Next topic is hard and soft acids and bases. In hard acid base reaction, according to Lewis concept, involves the reaction between the donor B and the acceptor A to form the complex AB. The formation of the stable complex between the donor B and the acceptor A depend upon the nature of the species A and B involved. It has been since long that certain ligands form more stable complexes with metal ion, such as silver positive, silver 2 positive, platinum 2 positive, and platinum 2 positive. On the other hand, certain ligands form stable complexes with metal ions such as aluminium 3 positive, cobalt 3 positive, and platinum 4 positive. Based upon the preferential bonding, the acid and bases have been classified into two groups via class A and class B according to their preference. Class A metal include alkali metals, alkaline earth metals, lighter and more highly charged ions. For example, titanium 4 positive, chromium 3 positive, aluminium 3 positive, iron 3 positive, cobalt 3 positive, etc. Hydrogen ion H positive. Class B ions include heavier transition metal of second and third transition series, cadmium 2 positive, mercury 2 positive, platinum 2 positive, platinum 2 positive. Heavier transition metal in lower oxidation state, mercury 2 positive, copper positive. Low valent metal ions such as zero valent metal in metal carbonyl. Depending upon the type of metal ion, ligand can also be classified as class A or class B, depending upon their preference. Class A ligand include molecules or ions with donor atom NOFCl. It is important to note that class A ligand prefer to form strong complexes with class A metals. Class B ligands includes molecules, ions with donor atom phosphorus, arsenic, sulfur, iodine, etc. Class B ligand prefer to form complexes with class B metal ions. It was in 1963 Pearson coined the term hard and soft acid and bases for class A and class B metal ions and the ligands respectively. Accordingly, class A metal ions are referred to hard acid while class B metal ions are referred as soft acids. Similarly, class A ligands are named as hard bases whereas class B ligands are termed as soft bases. In summary, according to Pearson, class A acids are hard acids, class B acids are soft acids, class A bases are hard bases, class B bases are soft bases. Next topic is classification of acids and bases as hard and soft. Pearson observed that it is possible to correlate acid and base interaction on the basis of hard and soft acids and bases. He observed that type A metal ion, i.e., acids were small, compact, non-polarizable, and these preferred ligand, i.e., bases that were also small and less polarizable. He called these acids and bases as hard. On the other hand, the type B metal ions and the ligands they prefer appear to be larger in size and more polarizable. He described these acids and bases as soft. Pearson generalized the acid-base relationship and expressed that hard acid prefer hard bases and soft acid prefer soft bases. Hard acid are cation of smaller size. Hard acids are cation of higher oxidation state. Hard acid are molecules cations with lesser number of valence electron. Hard acid holds the valence electron tightly and consequently are not easily polarizable. In summary, hard acid bind strongly to a proton. Hard acid are small sized, compact, and are not easily polarized. Soft acid are the cation of the large size or heavily elements. Soft acid are cation of lower charge. Soft acid are the molecules ions with larger number of valence electron. Soft acid do not hold the valence electron tightly and therefore are easily polarizable. In summary, soft acid are large-sized and easily polarizable ions molecules that bind strongly to highly polarizable ion molecules. It is important to note that there is no sharp division between hard and soft acid. There are a number of Lewis acids that are neither too hard nor too soft acid. Such type of acid that are neither hard nor soft are called borderline acids. Borderline acids have properties which are intermediate between that of a hard acid and a hard base. In case of borderline acid, the property such as size, oxidation state, and polarizability of the cation molecules are neither too low nor too high. On the other hand, soft acid will show the opposite trend and the following order of preference: binding donor atom ion within a observed I negative have greater affinity than Br negative, then Cl negative, then F negative. Classification of bases. Hard acid bind strongly to the proton. Hard bases contain donor atom of high electronegativity. The donor atom in hard bases possess low polarizability. The hard bases are not easily oxidized. Hard bases contain empty orbitals of high energy. In summary, hard bases binds strongly to a proton. The donor atom in case of hard bases is of high electronegativity and of low polarizability. Soft bases contain donor atom of low electronegativity. Soft bases contain donor atom of high polarizability. Soft bases can easily oxidized. Soft bases are associated with empty orbitals lying in low energy orbitals. In brief, soft bases contain less electronegativity non-metals. The donor atoms in such bases possess donor atoms that are easily polarized. Just as these are borderline acids, these are borderline bases also. The properties of borderline bases are in just those of the soft and hard bases. It is important to note that the categories are not rigidly divided. For example, the halide ion from a series form the very hard fluoride ion, though the hard borderline chloride ion to the borderline bromide ion and the soft iodide ion. The soft acids, also known as class B metal ion, are the group of the metal ion that are in low right of the periodic table. Pearson HSAB principle. Pearson proposed a simple rule for predicting the stability of coordination compound formed by the acids and base. This rule is quite often named as HSAB principle. According to Pearson HSAB principle, hard acid prefer to bond with hard bases while soft acid prefer to bond with soft bases. It is important to note that hardness and softness of acid and bases refer to only to hard interaction and soft interaction. It is by no means related to the strength of acids and base. For example, both F negative and OH negative ions are harded bases, but the basic strength of OH negative ion is almost 10 raised to power 13 times of the F negative ion. Applications of HSAB principle. Pearson principle of HSAB has a number of applications in inorganic chemistry. Some of these are discussed below. First application is stability of the complexes. We have already noted that hardness and softness of an acid and bases are related only to hard and soft interaction. Hardness and softness of acid and bases has nothing to do with the inherent acidic or basic strength of the acid or the bases. For example, both the OH negative and F negative ions are hard bases, although OH negative ion is for the stronger a base than the F negative ion. In fact, OH negative ion is 10 raised to power 13 times more stronger a base than F negative ions. However, in HSAB principle, both OH negative and F negative ions are at par with each other. Pearson in 1963 explained the relative stability of the coordination complexes on the basis of HSAB principle. Let us consider a general reaction between a Lewis acid and a Lewis base. A is Lewis acid, B is Lewis base that form a complex AB. The complex AB will be most stable if A and B are either both hard or both soft. The complex AB will be less stable if A is hard or B is soft, or if A is soft, B is hard. For example, a complex between a soft acid Ag positive and a soft base iodine negative ion is quite stable in contrast to a between a soft acid silver positive and a hard base fluorine negative. Similarly, the reaction between lithium iodine and cesium fluoride resulting in the formation of lithium fluoride and cesium iodide constitute an interesting example suggesting the preferential stability of soft and hard combination. Lithium iodide plus cesium fluoride that gives lithium fluoride and cesium iodide. In lithium iodide, hard soft interaction takes place. In cesium fluoride, soft hard interaction takes place that result into hard interaction in the LiF, and soft interaction is cesium iodide. The question is why cobalt hexafluoride complex is more stable than cobalt hexaiodide. In both the complexes, the oxidation state of cobalt is 3 positive. Cobalt 3 positive is a hard acid. Therefore, its combination with the hard base F negative leads to the formation of cobalt hexafluoride, which is a hard interaction. On the other hand, combination of cobalt with a soft base leads to cobalt hexaiodide, which is a hard soft interaction. Classification of acids and bases. The acid and bases can be classified as hard and soft depending upon their preference for hard and soft interactions. Let us consider the following reaction. RH positive plus CH3Hg positive, that gives CH3Hg. B positive plus H positive. We have already known that H positive is a hard acid, whereas CH3Hg positive is a soft acid. If B is hard base like ammonia, the reaction on the left hand side will be preferred. Conceptually, ammonia will be written as NH4 positive, that gives NH3 plus H, which means that formation of NH4 positive is preferred because of hard acid and hard base. Few examples are also given below of the same effect. One example is also taken. Similarly, an acid A can be classified as hard or soft depending upon the direction of equilibrium as AF plus SCN negative equilibrium equation, that gives ASCN plus F negative. We know that F negative is a hard base and SCN is a soft base. If A is soft acid like silver ion, then the Bohr reaction is forward is favored. AgF plus HCN, that gives AgHCN plus F negative. It is important to conclude that at this stage, Lewis acid Lewis base reactions are governed by two independent principles: strength of acid or base, softness and hardness of acid or base. The definition of hardness primarily uses the idea of polarizability, which states that less polarizable species is hard and more polarizable species is soft. For ions of similar charge, the ratio of radius should be used to assess the relative polarizability. Using HSAB principle does not take into consideration the quantitative idea of relative hardness and softness of the species. In summary, major limitations of HSAB principle are: HSAB principle is too general and without any qualitative scale of measurement. HSAB principle does not take into consideration of acidic or basic character of the compounds. HSAB principle fails to explain the feasibility of the reaction, that is CH3 positive plus H2 that gives methane plus H positive. Thank you so much.